Example 2. N moles of an ideal gas undergoes isobaric process at pressure P. The initial temperature is Ti, and the final temperature is Tf. Please answer the following questions. A. Please derive an equation to calculate the entropy change if the molar heat capacity at constant pressure Cpm is independent of temperature. B. Please calculate the entropy change if the molar heat capacity at constant pressure Cpm is a function of temperature. Cpm is equal to 25.9 plus 8.66 times 10 to the negative 3 T minus 2.16 times 10 to the negative 6 T squared plus 1.79 times 10 to the negative 10 T to the third power. The initial temperature is 500.0 Kelvin and the final temperature is 3000.0 Kelvin. Well, let's work out the answer for part A. Well, since we want to calculate the entropy change of a process, therefore, one starting point is to use the definition of delta S. Delta S is defined as Q reversible over temperature in Kelvin. Q reversible represents the heat of a reversible process. We cannot use this equation directly because the temperature is changing. However, we can use a small trick to calculate delta S with this equation. What we do is, from the initial temperature Ti to the final temperature Tf, we can cut it down into very, very tiny pieces. In more accurate term, we should call that infinitesimal change of temperature, because the change of temperature is so small. When we calculate, we can assume the temperature is constant. Let me put this down. The reason I did not use D, because Q reversible is not a state function. Then, as we know, for Q reversible at constant pressure, it is equal to the change of entropy. Okay, so if we want to calculate the change of entropy, we can have a very simple equation to use. Then we can integrate both sides of this equation. We will get delta S. Because both N and Cpm are constants. Therefore, when we integrate, we can take them out. On the left side, this is delta S. On the right side, 1 over T dt integration is equal to natural log T. If we consider the limit of initial temperature and the final temperature, we will get natural log Tf over Ti. This will be the answer for part A. Well, from this equation, we can also link back to the 3 qualitative rules to predict the entropy change. Remember, when we increase the temperature, the entropy increases. We can say the same conclusion from this equation. When we increase the temperature, the final temperature is larger than the initial temperature. Therefore, the ratio between Tf and Ti is larger than 1. Natural log Tf over Ti will be positive. Therefore, delta S is positive. That means the value of the entropy in the final state is larger than the value of the entropy in the initial state. Now let's look at part B. When we calculate part B, we cannot use the equation we derived from part A. Because in part A, when we derive the equation, we assume that CPM is independent of temperature. But for B, CPM is a function of temperature. But don't worry, when we work out B, what we do is we will start from here instead of from here. Because CPM is a function of temperature, what we do is we just plug in the expression of CPM into this integration. Then let's see what we can get. N is a constant, therefore we can take out N. To integrate, we have to separate each term. These three terms can be simplified. This term, we can get the integration directly. Oh, sorry. For this second term, T and T will cancel. Then we can integrate each term. Well, since we get the equations, we can plug in the values to get the answer. Oh, I just realized that I did not give you the moles. Well, let's assume that the moles is 1. The final temperature is 3000 Kelvin. The initial temperature is 500.0 Kelvin. We can plug all numbers into a calculator, we will get our final answer. Well, let me summarize. If CPM is independent of temperature, you can use this equation to calculate the entropy change. But if CPM is a function of temperature, you have to integrate. That's the way you get your answers.